Hello, my name is Nitin Vaidya from Georgetown University, and this talk is about distributed optimization, in particular security and privacy in distributed optimization. So the outline for the talk is that I'll start with some background and define the problems for you somewhat more formally and give you some intuition behind the solutions that we have. Given the short time of the talk, we won't be able to go into too much detail of the answers or the proofs or anything like that. So here's an example where the problem of distributed optimization appears. Imagine that we have three people trying to meet somewhere for dinner, and this map shows where those three people are starting. And each of us in this example is wanting to meet at a particular location that they may prefer versus others. And you need to decide a location that is good for everybody. And the question is, how does one define a location that's good for everyone? One possible way is to define a cost function. For example, if we label these three people or these three agents as number 1, 2, and 3, then agent number 1 has a cost function f1 of x, where x is the location where we meet, and f1 is the cost for agent number 1, f2x is the cost for agent number 2, and so on. And then the objective, or a reasonable objective, would be to pick a location x such that the total cost f1 plus f2 plus f3 is minimized at that location. So in a sense, the sort of desired solution in this case is perhaps the argmin of summation fi of x, where the summation is over all agents I. Argmin denotes the argument x that minimizes this total cost function. These kinds of cost functions appear in many, many different settings. Here is another example where it appears, in particular machine learning. So consider the setting where the data on which we are training machines is distributed. So in this example, there are 4 agents over which the data is distributed. These 4 agents could be 4 different cell phones that are collecting data for each of the users of those cell phones, or these could be hospitals that have their own patient databases, things like that. Given that the data is distributed, somehow these agents must collaborate to learn or to train a machine or a neural network. And the question is how. There are many different ways to do it. One sort of a simplest way would be to bring all the data to one location and then use the data collectively to train a machine. But we are looking at more distributed solutions of this problem. They exist already in practical use. But coming back to the question of this talk, distributed optimization, in case of machine learning, we have to think about this data as defining a cost function that in the machine learning setting is often called loss function. So f1 of x is the loss function for agent 1, f2 of x is the loss function for agent 2, and so on. And the objective of machine learning or training a network, neural network, would be to minimize this global or the total loss over all the agents. So again, in this case, the goal is to find parameters for the machine that are called x here, such that the total loss over all the agents is minimized. So there are many examples of these cost functions appearing in a variety of settings, rather large diversity of settings. And because of that, there is a lot of research on optimizing functions of this kind distributedly over the last 30 years. But here is a very simple sort of reminder of how optimization works. Suppose that the cost functions we are dealing with are convex. F of x is the global cost over all the agents I. And let's say this picture illustrates the global cost function. In this example, x is 2-dimensional. So imagine the horizontal plane is the x vector x of dimension 2, and the height of this curve is the function value at that x. So the way you optimize these cost functions, we start somewhere initially. Let's call it x of 0. So x0, 0 in bracket denotes the initial value or the initial guess of the value of x that minimizes the global cost. And then knowing x0, we will compute x1, then x2, then x3, and so on. And with time, we will approach the value of x that minimizes the cost function. And the gradient method updates x as this equation shows here. Suppose we know xk already. Initially, we know x0. Then xk plus 1, the next value of x, the estimate x, is computed as xk minus the gradient of the global cost function and multiplied by, in this case, lambda. That's often called the step size. Lambda might depend on k. In this equation, it doesn't, but in general, it can. But the key to this computation is knowing the gradient of the global cost function. Because f of x is summation of fi of x, gradient of fx is also equal to summation of gradients of each of the individual cost function. So the summation over the gradients of individual cost function needs to be computed for this. And given that each agent knows its own cost function and only its own cost function, it cannot really compute the grade summation directly. So they have to talk to each other to achieve that goal. So like I said here, this requires some sort of distributed computation so that we can compute the summation of the gradients to implement the algorithm on the previous slide. And there are many ways to achieve this goal. There are several different algorithms people have proposed, in particular in two different settings. One setting is the so-called peer-to-peer setting, which is the illustration on the top left corner of this slide. In this picture, 1, 2, 3, 4, and 5 are different agents in the system, and they're connected by some network. And in this network, each agent can directly communicate with only its neighbors in this network or in this graph. The other architecture is a server-based architecture. In this case, there is a server that everybody trusts that is helping the agents achieve this global optimization over the global cost function. In this illustration, 1, 2, and 3 are the agents that can communicate with the server directly, and the server helps them achieve the goal of optimizing the global cost function. Even though distributed optimization has been looked at in both the settings, and even in our work, we have looked at both the settings. For this talk, to keep things simple, we will look at the server-based architecture. So here is a very simple algorithm for optimizing this global cost function using a server. The server is the one that will keep track of the estimate of the minimum of the global cost function. Initially, we called it x0. We put x0 in the brackets on the previous slide. Here, it's written as a subscript, but the same idea. So the algorithm is very simple. The algorithm is iterative, as we saw on the previous slide with that equation, xk plus 1 computed using xk. So each time we use that equation is one iteration of the computation. In a distributed setting, the server will send the current estimate xk to the different agents, in this case, 3 agents. And each agent, having received the xk value, will compute its own gradient of the cost function of the gradient of its own cost function. So for example, agent 1 will compute gradient of f1 at xk and send it to the server or upload to the server. And when the server receives all these gradients, it can add them up and perform this computation locally because it knows all the gradients. It can do that summation shown in red here, and that's how server can compute xk plus 1. If you repeat this step several times, as time goes forward, xk value converges to the argmin of the global cost function, summation of fi of x. It's a fairly simple algorithm. In practice, this particular algorithm is not used too often because it's not efficient, it's synchronous, which can slow things down. So there are many variations that have been used in practice. There is something called stochastic optimization that's used commonly. There are asynchronous algorithms, and there are a few other optimizations and variations that have been looked at. For the purpose of this talk, this simple solution will suffice. So in our work, we are looking at two distinct challenges in the context of distributed optimization in both the server-based implementation or server-based architecture and the peer-to-peer architecture both. But again, let's look at them in the context of the server-based architecture for now. So in this setting, again, we have a server with many agents, and the algorithm that we saw on the previous slide relies on these servers, or rather these agents, to cooperate, to do the right thing by uploading the gradient of their own cost functions correctly. But if we want to achieve security, then we have to allow for some of these agents to be compromised or faulty and provide essentially bad or incorrect information to the server. In this case, it would be a bad gradient. So in this example, the red agent, number 3, is a bad agent or a faulty agent or a compromised agent. and it may upload incorrect gradients for its cost function F3. Now, if the server gets incorrect gradients, then this computation at the bottom of this slide will not be done correctly because it doesn't have the right gradients for the cost functions. So the question then is, what do you do when these agents are behaving badly? How do you do global optimization? And what does it even mean to do global optimization correctly when sub-agents are faulty or compromised? The dual problem of fault tolerance or security is privacy. Now, in this privacy setting, let's pretend that the agents are actually all the good guys, but the server may be a bad agent that is trying to learn something about my cost function. And the question that we're asking here is, can we perform this goal of optimizing the global cost function while preserving some notion of privacy for these agents? So we'll talk about fault tolerance or security first, and then I'll briefly talk about privacy towards the end of the talk. So we have been working on fault tolerance optimizations since roughly 2015. This line of work builds on previous work that we have done and others have done on Byzantine consensus, where the goal is to agree on something that depends on inputs at different agents. Those inputs might be scalar quantities or vector quantities. The goal for today is optimization, which is a generalization on the notions of consensus. So we use the Byzantine fault model in our work, which says that there is no constraint on the behavior of the faulty agent. So faulty agents can do whatever they want. There are no limitations on what they can do. So let's take the example of the rendezvous problem that we saw earlier, where the goal is to meet somewhere. If one of the agents was faulty, let's say number 3 at the bottom of the screen here is faulty, then it might pick a somewhat contrived cost function, which is minimized at a location where the agent 3 wants to go and has high cost, let's say, everywhere else. If that's the kind of cost function that agent 3 pretends to have, then when we minimize F1 plus F2 plus F3 and meet at a location where the global cost is minimized, what's going to happen is that we're going to end up meeting at the location of preference of agent 3, because agent 3 picked this cost that is very high everywhere but the location or in the vicinity of the location where that agent wants to meet. And in effect, the agent can bias the output of this distributed optimization arbitrarily. Similar such things can happen in other contexts as well. Let's say in machine learning, if you're cooperating to train a neural network together, then agent 2 can pick basically bogus data or supply bogus gradients, bad gradients, such that it can bias the choice of parameter X that we converge on as a result of this distributed computation. So it can essentially tamper with the decision or the outcome of the distributed training of a neural network here. So clearly, having some faulty or compromised agents in the system is bad, and we want to tolerate those agents, or you want to detect those agents. So those are the 2 alternate solutions. Detection of a faulty agent requires us to look for behaviors that look abnormal. And when they look, the behavior looks abnormal, we can remove the agent from the system. Tolerance says that we don't necessarily try to detect or identify a faulty agent, and yet we are able to produce good or reasonably good output. So for today, we are not focusing on detecting or identifying faulty agents. We will not try to identify which agents are behaving badly, but we still want to produce the correct outcome from this computation. So before we can define what correct means, before we can solve the problem correctly, we need to define what correct means. And that brings us to this question: what should be the objective of fault tolerant optimization? So when we started working on this several years ago now, there wasn't a formulation of this problem. And so we decided that this was a good objective for fault tolerant optimization. So we set out initially to optimize the cost of all the agents, the aggregate cost of all the agents. But now some of the agents are allowed to be compromised or faulty. And it seems that minimizing cost over everybody is not a good solution anymore because of the examples I just gave you. Then a better answer may be to try to optimize the cost of just the good agents, right? Because some of the agents are bad. Maybe we don't care about the cost of the bad agents, but we want to minimize the cost just for the good guys. So let's say that in a given execution of the system, set G denotes the set of all the good agents in the system. They can change in different executions, right? If I run the system today, agent number 1 may be faulty. Next year, it might be agent 2, or somebody else running a system like this may have agent 2 faulty. So let's say G is the set of faulty agents. Then we want to minimize the cost of just the good agents. So summation Fi of X, but this time I are just the good agents, not all the agents. So then we can try to use the solution that I showed you earlier, where we had the server maintaining the estimate. It sends the estimate to all the agents. The agents had to upload the gradients. To solve this problem exactly as written here, what you really want are gradients of just the good agents. The trouble is that the parameter server actually doesn't know who the good agents are. Like I said earlier, we are not trying to identify a particular agent as being faulty. We just want to do the right thing. And given that the server doesn't actually know which agents are good or which agents are bad, it needs to do something to try to mitigate the impact of the bad agent. And we are going to look at an algorithm where, as I will show you later, the server will use a filter of some kind that takes the gradients received from the agents, applies a filter, and then uses the outcome of that filter to compute the next estimate. And since our initial work on this problem, people had designed many, many different filters, and I'll show you one of them today. But these filters differ in their complexity and the performance they can achieve. But this particular structure is quite effective, works for many different versions of this problem. But coming back, the question again remains that even if I have a solution like this, how do I know it's behaving well? What does it mean to behave well, or what is the notion of correctness? Like I told you, the correctness notion we defined somewhat arbitrarily was to minimize the cost over all the good guys. But the question is, can you actually do that, right? It's good to ask for this, but can you do it? So the answer, whether this is achievable or not, depends. It depends on the functions themselves. So if these cost functions, Fi of X, are completely arbitrary, meaning cost function F1 of X reveals nothing about anybody else's cost function, we will think of these cost functions as being independent. So knowing any set of cost functions tells you nothing about cost function of other agents. So even if I know the cost functions of all the agents but one, I learn nothing about that remaining agent. So this is an informal definition of what independence means. But if you have independence like that, then actually we cannot achieve this objective of minimizing the cost of just a good agent. On the other hand, if we have redundancy in the cost functions, then that objective is achievable. As a trivial example, suppose that we are in a system where, for some reason, all the cost functions are identical, meaning F1 of X is equal to F2 of X equal to F3 of X. You have complete replication, basically. Then it's easy to see how one can solve this problem trivially, in fact, because each agent can just minimize its own cost function. And we would have optimized the global cost function too, because everybody has the exact same cost function. But this is a spectrum of possibilities, independent cost functions on one end, and at the other end, we have enough redundancy. And I'm going to talk about the redundancy part a bit more today. And then there is, this range in between where you have maybe some redundancy, but not enough to solve this problem. And I'll tell you a little bit about both the extremes, and hopefully you get a feel for the space of problems that exist, and something about the solution space as well. So let's talk about the independent functions first. So here's an example where the argument X that you're trying to determine is a scalar. So in this example, we have three agents standing on the street, Constitution Avenue in Washington, DC, and they want to meet somewhere on this street. And we're trying to decide which point or which X location on the street that they want to meet at. Like I said earlier, the goal is to minimize the cost, the total cost over just the good agents. So let's say there are three agents, like this picture shows, and I'm agent A on the left side of this picture. I don't actually know that agent C is faulty or agent B is faulty. I know that there may be one agent faulty because that's the desired sort of parameter of number of faults we want to tolerate. So the algorithms we're going to discuss today will limit how many bad agents are there in the system. And for this example, we are limiting the number of bad agents to 1. So if agents A and B are the good agents, then we would want to minimize the cost over just the agents A and B. In this picture, these curves here are the cost functions. For example, for agent B, this is the cost function. And as you step from the current location of agent B to the left or right, the cost increases as a function of how far you're going from the current location of the agent, and similarly for the other 2 agents as well. So if agents A and B are the good agents, then you want to minimize the cost over A and B together. And the optimal value of X will be somewhere between the current locations of A and B, as pointed by this green arrow. On the other hand, if A and C are the good agents, with B being the bad agent, then you want to minimize the cost over A and C, which would be minimized somewhere here. Now, agent A actually does not know whether C is faulty or B is faulty. And given that the outcome has to be different for the 2 different situations, there is no way agent can correctly choose the minimum over just the good guys, the good agents. And that the simple example tells you that the goal of minimizing cost over just the good agents actually is not achievable when some of the agents may be compromised. This is a trivial claim, but then that begs the question as to what should you do when the cost functions are independent. If we cannot achieve our original goal of minimizing the cost over just the good agents, then we cannot just declare defeat. We have to do something. And the question is, what can you do? What you can do is to approximate this goal. And I'll get to what I mean by approximation in a few minutes, but I want to take a detour into the other end of the spectrum here and take that case of enough redundancy and define for you what that means. So if you have enough redundancy, then it is in fact possible to achieve that goal of minimizing the cost over just the good guys. We can achieve it exactly. The question then, of course, is what does enough redundancy mean? And here is what I mean by enough redundancy. So let me introduce some notation. Suppose that our system contains n agents. So n may be, for example, 10. And we want to tolerate up to t bad agents. So for example, t might be equal to 2. And our ideal goal is to minimize the cost over just the good agents. So there are at least 8 good agents. There may be 9, there may be 10. We just don't know how many, but we know it's at least 8, and we don't know who. But we still want to minimize the cost over all the good agents without knowing who they are. And here is how I'm going to define the redundancy. So redundancy condition here says that the aggregate cost of any n minus 2t agents, so in my example, n is equal to 10, t equal to 2, so n minus 2t is equal to 6. So if you take any 6 agents and minimize the cost over those 6 agents, 6 good agents actually, 6 non-faulty agents. So if you minimize the cost over just the good any 6 good agents, then the cost is minimized exactly at the same value of x, where the cost over all the agents is minimized. So let me repeat that. If you take the summation of the cost fi over all the agents g, and it's minimized at, let's say, the value of x equal to x star. Now, if you take any n minus 2t good agents, in my example, that would be 6, and minimize the cost of just those 6 agents, the aggregate cost of those 6 agents, that's also minimized at x star. And this is true for every set of n minus 2t good agents. That's what I define as redundancy here in my cost functions. If this redundancy condition is true, then we can in fact compute that x star correctly without knowing who the good agents are. Now, this particular condition may seem a little bit contrived and a little bit too stringent, but turns out it's not necessarily difficult to achieve this condition in practice. So as an illustration, let me consider the problem of sensing. So let's imagine that there are cameras looking at an object in the sky. And if you just take one picture of the object, you cannot really tell whether it's an enemy aircraft or a friendly aircraft, or is it a bird or a rocket or a missile or whatever, right? It's not always easy from one observation to infer what you're looking at. But if you have enough cameras on the ground from different angles, let's say 4, then when you combine them all, you can tell, oh, this is what I'm really looking at. Now, if some of these cameras or the sensors are faulty, then you're going to need more sensors to tolerate the failure. And intuitively speaking, what this condition is saying is the following. If I have 10 sensors on the ground that are looking at the object in the sky, and if I allow 2 of them to be faulty, then what this condition is says that as long as any 6 good sensors are sufficient to identify the object correctly, I will be able to identify the object correctly. Where I'm going to translate the observations of the sensor into a cost function that I have not specified for you here. But again, intuition is that I'm trying to achieve a particular objective, such as training a neural network to compute the right set of parameters. And we know that if I have data from all the good agents, I will be able to compute the right set of parameters. This condition requires that you should be able to compute the right parameters even with just n-2t good agents. And that requires redundancy in my data set, which translates into redundancy in the cost function. So like I said earlier, we will use algorithms of this kind in today's talk to achieve this notion of fault tolerance. So the goal of fault tolerance, again, is to optimize this global cost function at the bottom, at this end of the sentence here, summation fi of x, where all the I are all the good agents, but we don't know who the good agents are. And what the server is going to do is to talk to all the agents, including the bad ones, because it doesn't know who they are. And the algorithm, as we saw on the left-hand side, says that the server has an estimate of the value x. It sends to all the agents, collects their gradients, and now instead of just adding up the gradients, it's going to filter them. And then having done the filtering, then it will take this step. So the question is, what is the filter gradient? How do you compute this value? And there are many filters. There is more than one that my group has proposed, and others have proposed a few also by now. But here is the one that we will discuss today. It's one of the simplest filters you can design. So the server receives n gradients in any given iteration of the algorithm. So the gradient in this setting is, you can think of it as a vector. It's pointing in a certain direction. The x could be a high dimensional parameter, right? In neural networks, they could have hundreds of, not even thousands or millions of parameters. If you're trying to meet for dinner, it could be a 2-dimensional coordinate, x and y, right? But in general, it's a vector. So it's an arrow pointing in a particular direction. So the arrow has a direction and length. The length is what is called the norm. And what the algorithm, the filter here is what we call the comparative norm filter, but here is what it does. It computes the norm, the length of all the gradients, and takes the largest t gradients. In our example, n was 10, t equal to 2. If t equal to 2, it takes the largest 2 gradients and make their norm equal to the t plus 1th gradient. For the numerical example, I'm choosing t to be equal to just 1 to keep things simple. So I have, in this case, 3 gradients, and t equal to 1, meaning I want to tolerate 1 bad agent. So I compute the norm of the 3 gradients. They happen to be 1, 3, and 2. 3 is the largest norm. I'm going to make it equal to the t plus 1th largest norm, which is 2 now. So that's achieved by scaling the second gradient by a factor of 2/3. So the first gradient remains unchanged because it's not the largest gradient, or it's not among the largest t gradients. Same is true for gradient number 3. But gradient number 2 is in the largest t gradients, and it gets clipped. It gets scaled down so that length is equal to 2. So I have to multiply it by a factor of 2/3 and then add them up. And this is what I mean by the filter gradient. It's actually an aggregate over all the agents, but some of the gradients have been modified or have been scaled or clipped. And then we do this step to compute the next value of x. And then you repeat. And if we repeat this iteration long enough, then we compute the exact optimum value of x that minimizes the global cost over all the good agents. We do make some additional assumptions about how many faults are in the system. So if you have too many faults, of course, this algorithm cannot behave correctly. So we assume 2 conditions. There is a bound on the number of faults that we allow, the number of bad agents that we allow, and then we require this redundancy condition that we saw on the previous slide. Turns out that this particular condition that we also call 2t redundancy condition 2T because what I'm asking for is that if you exclude any 2T agents, any 2T good agents, the remaining good agents can still solve the problem. And that's what we call it the 2T redundancy. So this 2T redundancy condition is sufficient, as illustrated by the solution I just presented, but it turns out it's also necessary, meaning that if you want to truly solve the problem of minimizing the global cost function over the good agents exactly, then you must have this condition true. If the condition is false, then the problem is actually not solvable exactly. So these kinds of redundancies, like I said, the condition looks a bit stringent, but it's not necessarily difficult to achieve this condition. If not exactly, then approximately. In the case of machine learning, the data is often correlated, right? If not always correlated. So it's almost never the case that the data at agent number 1 is completely independent of agent number 2. And given that dependence across data available to different agents, it seems reasonable that we don't need data from everybody to train a good neural network. If you take an extreme case of this, then you get a situation where all the agents actually have the same data, or more generally, when they draw samples of the data, they're drawing it from an identical distribution. So each agent, if you were to pick a random data item, it will be drawn from the same distribution. And so in effect, you have full replication. All the agents are identical in their expected behavior. So if you look at their expected cost function, the expected cost function is identical for all of them, or the expected gradient is all identical to all of them. But if you compute the gradient at any one iteration, and I'm sort of skipping details here, but in stochastic optimization or stochastic learning, these gradients are not exact gradients of the cost function, but estimates that may have errors, but the error is zero mean and has some nice, you can assume, or we tend to assume some nice bounds on the variance of the gradients. But long story short, in the machine learning setting, if all the agents have access to identically distributed data, then the solution I presented here can be applied to that setting as well for the stochastic gradient case. And in fact, this particular version of the problem has been looked at by several other research groups too, and they have obtained their own versions of the filters for this particular problem. For lack of time, I won't go into this in too much detail. So coming back to this picture, we set out to optimize the global cost or the total cost over just the good agents in the system without knowing who the good agents were. And this was our objective. Now, if you were to solve this problem, you might define a different objective. There may be other objectives that make sense, but this is the objective that we define. And then the question was, when can you achieve the objective? What I showed you is that if the functions are independent, then this objective is unachievable, but we can approximate it, as I'm going to show you on the next slide. Or if you have a lot of redundancy, and I told you exactly what enough redundancy means, I gave you a tight condition on redundancy, under which you can actually solve that problem exactly. So what does approximation mean? Recall our goal. The goal was to minimize the total cost function over just the good guys, compute the argmin of summation fi of x. But that's exactly equal to argmin of summation of 1 over g of fi of x, where g here is the size of set g. So because we're multiplying each cost function by the same constant, the argmin actually does not change. But one way to think about the right-hand side is that what we're trying to minimize is a uniformly weighted average of the cost function of the good guys. Sigma fi of x was the goal. We are minimizing sigma alpha I fi of x, where alpha I happens to be equal for all I, equal to 1 over g. So to repeat myself, the goal that we set out initially is to minimize a uniformly weighted average of the cost function of the good agents. But I already told you that you can't do that with the example of those 3 agents standing on Constitution Avenue. So if that goal is not achievable, what can you do? Turns out that you can actually find the argmin of a non-uniformly weighted average of the cost functions. Even though uniformly weighted average is not achievable, non-uniform is possible. So I don't have a lot of time to get into the details of this, But this is what you can do for the case where the argument. Actually, let me just get to this slide. This is what you can achieve for the setting where x is a scalar. In general, x is a vector, but I'm just giving you results for x equal to scalar. What we can output is the argmin of a cost function that looks like this. It's a weighted average of a phi of x, where the weights are alpha I. But alpha I are not going to be uniform, at least cannot be guaranteed to be uniform. But what you can guarantee is that if you have n agents of which we are trying to tolerate t bad agents, then at least n minus 2 t good agents have weight that is roughly uniform. The weight is more than 1 over 2 times n minus 2t. So again, we set out to achieve alpha I to be uniform vector. But this is what I can achieve. I can guarantee that at least n minus 2t agents have weight that looks like this. It's close to uniform, not exactly uniform. But what about the other good agents? In general, there may be t bad agents in the worst case, and at least n minus t good agents. What about the other t good agents? It turns out that in the worst case, there could be t agents who get 0 weight, which is to say, there are t good agents in the worst case whose opinion, whose cost function does not impact the decision of this particular algorithm that we have, that I've not told you about. But we can also show that no algorithm can do better, meaning that for any algorithm for this problem, you have to allow for the possibility that t of the agents may get weight 0 in the final outcome, meaning they have no impact on the final outcome, and no algorithm can do better. So in a sense, the results we have are tight in a particular way. Given that we only have 45 minutes today, I'm going to have to leave this here. Let me just say that this is a very rich space of problems. We have some interesting work so far, but there is room for a lot more. And I encourage you to look at our papers on our website if you have interest in digging into this further. So let's skip over that. So I briefly mentioned earlier that security or fault tolerance is one of our goals. The other goal is privacy. And let me speak to that just for a couple of minutes. I'm going to wrap up soon because I think I'm running out of time. So now we are not going to assume that the agents are bad in the sense of tampering with anything, but they may be curious to learn somebody else's data. So if you're agent number 1, you might want to learn the cost function of agent number 2. Or if it is machine learning setting, agent number 1 may want to learn the data that agent number 2 has. And similarly, the server may want to learn something about the agent. The server may want to learn cost function f1 of x, or in machine learning, server may want to learn the data of this agent. And the goal now is to try to sort of prevent the server from learning information like that, or the other agents for that matter. But if we use the algorithm that I presented earlier, where the server is sending the estimate to the agents uploading the gradients, it's easy to see that if you get enough gradients for a polynomial cost function, then you can eventually infer the polynomial cost function. Now, for any cost function, you can always find a polynomial of sufficiently high degree that approximates that cost function. So what this is saying is that if I get enough information in the form of gradients, the more gradients I get, the more I learn about the cost function. And we want to try to mitigate this kind of compromise in privacy. So people have looked at this particular problem for many, many years. There are many methods, and they all have their pros and their cons. What I'm going to tell you about very quickly is our approach, which is motivated by differential privacy and also by secret sharing. Secret sharing is a very different technique from differential privacy. But when you combine the intuition behind those two, you get the solution that we have. And in effect, what we do is to add what we call cancelable noise in the communication between the agents and the servers. So for our solution to be used, the system needs to contain more than one server. One server is not sufficient to utilize our solution. There must be multiple servers. So that's a cost we are paying, but we gain something in return. So the idea now is that instead of the agents talking to just one server, they're going to talk to multiple servers, in this case, 2 servers. Both the servers are going to perform an algorithm of the kind that we did earlier, where the servers maintain their own estimate of the minimum, and they share the estimate with the agents. Agents compute gradients and upload to the servers. And something very analogous happens here as well, with one additional step that now, because there are two servers, the two servers need to talk to each other as well to achieve consensus among themselves, because they have their own estimates of X and they somehow need to converge. And there's a notion of a consensus algorithm between the servers that we use. But let's focus on the step where the agents are talking to the servers. So let's say that the agents, here's an agent number 1 on the left-hand side. In our example, has to upload a gradient to the server. In this picture, actually, is going to upload the same gradient to both the servers. But now, instead of uploading the same gradient to both the servers, what the agent does is to add some noise to it. So it doesn't send the actual gradient of its cost function to either of the servers. It adds noise epsilon1 to the gradient sent to server 1. It adds noise epsilon2 to the gradient sent to server 2. But the noise is chosen not independently, but dependent, such that the noise cancels. Now, in this example, it may cancel in this single time step, meaning epsilon1 might be equal to minus epsilon2. But in general, it doesn't have to cancel in one time step. It could cancel over time, meaning over several iterations. And it has to cancel over all the servers that the agent is talking to. In general, it could be talking to more than 2 servers. So this noise just has to cancel over time and space, but it needs to cancel. So that's the key assumption we make in our algorithms to achieve correctness. Another way to visualize what's happening. So in this picture, I said that I'm uploading gradients and I'm adding noise to that. That's one view of the problem. The other more intuitive view of what's happening is the following. Imagine that the agent has a cost function. Let's call it f1 of x. Now I'm going to write that f1 of x as a summation of 2 different cost functions. Let's call those p11 of x, p12 of x. Here the indices is that p11, the first index, is the agent ID. We're talking about agent 1. And the second index is the server he's talking to. So p11x is a cost function that the agent 1 pretends to have in its communication with server 1. p12 of x is a cost function that agent 1 pretends to have when it communicates with server 2, such that the 2 cost functions add up to f1 of x. And what the agent is going to upload to the server are the gradients of these fake cost functions. So this agent is going to simulate 2 other virtual agents with these cost functions that are computed starting from the original cost function. Now, these cost functions don't have to be deterministic. There could be some randomness to them as well. But as long as this property holds in some reasonable way, either deterministically or in some expected sense or over a short time horizon, this algorithm should converge to the right answer. But the right answer is minimizing the global cost over all the agents. So the correctness is preserved by having this property where the cost functions add up to f1 of x, and similarly for f2, f3, or by making sure the noise cancels out over time and space. So correctness is not compromised at all. The algorithm behaves correctly, just as an algorithm that doesn't give you any privacy will behave correctly. But this algorithm gives you some notion of privacy as well. I put privacy here in double quotes because I'm not quite defining what I mean by privacy. But you can show some sort of precise properties about what sort of privacy you get from this particular solution. So this solution is not for all settings because we need multiple servers. Some of the other previous solutions actually don't need that. We may not give the same notions of privacy as some of the other solutions can give you. But this is one more sort of tool in the tool chest for achieving privacy for distributed optimization. So mathematically, sort of what underlies this solution is this idea that we are minimizing a convex sum. You know, if you assume that the initial cost functions f1, f2, f3 are all convex, then the summation of fix is also convex. And when we had these other cost functions, p11, p12, and so on, they may not actually be convex, but yet their sum is still convex. And as long as the sum is convex, the solution converges to the optimum of the sum. So the individual cost function actually don't need to be convex. So let me try to wrap up with this slide. We started with the goal of minimizing the cost over many agents, where the cost defines something that is context dependent. For the problem of rendezvous or meeting, it was the cost of going somewhere. For the machine learning setting, it's the cost of the loss function over the data that the agent has. And there are many other applications of this in cyber physical systems. But the goal is to minimize the global cost. In the case of fault tolerance, we said that we can't quite do this because some agents are faulty. And then we're going to minimize it, try to minimize the cost over just the good guys. And the solutions that I presented today use this notion of a gradient filter, but there are other solutions possible as well. And for privacy, same ultimate goal, minimize the cost function, but trying to preserve something about some privacy of the cost functions themselves. And the trick we use is what we call the cancelable noise. Let me acknowledge the work, the contributions of my students and postdocs. This work on fault tolerance was started by Lily Su's PhD thesis and continued by other people working with me since then, including Nirupam Gupta, who is a postdoc with me. And the work on privacy that I presented very briefly today is Sripad's PhD thesis. And the work is funded by several agencies, funding agencies, so let me acknowledge them as well. Again, thank you. The papers that cover the results I presented today and then many other results are available from my website.